Lecture 5, Triangulations and Simplicial Complexes, with an optional introduction to cell complexes. The building blocks for a simplicial complex consist of 0 simplices, which are zero-dimensional vertices, 1 simplices, which are one-dimensional edges, 2 simplices, which are two-dimensional triangles, as well as 3 simplices, which are solid three-dimensional tetrahedron. To distinguish between the boundary of a tetrahedron and the solid three-dimensional tetrahedron, we will use dark blue to denote a 3-simplex. So on the left here, I have the boundary of the tetrahedron consisting of just the two-dimensional faces, these 4 two-dimensional faces here, illustrated using light blue for the two-dimensional faces. But if we fill in to create a solid three-dimensional 3-simplex, then we will use dark blue to indicate it that it's been filled in, and so we have a solid three-dimensional 3-simplex, a solid tetrahedron. We can also have higher dimensional simplices. To create a simplicial complex, we start by adding zero-dimensional vertices. So our step 0 is to add zero-dimensional 0 simplices. So we just add a bunch of vertices. A collection of vertices is called a zero-dimensional simplicial complex. After our step 0 of adding zero-dimensional 0 simplices, we then go to step 1 of adding one-dimensional 1 simplices. So we can add a bunch of edges, but there are rules in terms of adding our edges. An edge must go from one vertex to connect to a different vertex. So I'm not allowed loops, so I can't have an edge that starts off at one vertex and goes back to the same vertex. That is not allowed, so no loops. We're also not allowed to have multiple edges, so I can't have many edges connecting the same pair of vertices. One of the reasons for this is if I label this vertex here V1 and this vertex here V2, I would like the pair of vertices V1, V2 to uniquely identify an edge. But if I have multiple edges connecting V1 and V2, then this set of this pair of vertices will not uniquely identify the edge. So if I have an edge, a vertex V and a vertex W, then I want to have exactly one edge between them, or at most one edge between them, so that I can then denote the edge using this pair of vertices. So a pair of vertices, that set, will denote the edge connecting those two vertices. So thus we don't want to have multiple edges, or we won't have this unique identification. We also don't want to have loops, since a pair of vertices would not indicate a loop. So we can add a bunch of edges. There's really no restriction in terms of adding our edges, except that the boundary of the edge, those two vertices, must already exist in my simplicial complex. So I can add edges that cross. That's no problem. There is not a vertex, so there's no vertex here. But we just need to draw these things somehow to connect them, and how we draw them, if we draw them, like this, that's perfectly fine. Crossing is perfectly fine. In the next lecture, we will look at creating a simplicial complex from data points. Data is usually high dimensional, so the chance of being able to draw the simplicial complex corresponding to your data, that you can draw it in the plane, will be very, very unlikely. So crossing edges is perfectly fine. I can add lots more edges. So adding lots of edges here, adding more edges, adding lots and lots more edges. I now have a one-dimensional simplicial complex. So in our step 1, we added one-dimensional, one simplices, where the boundary of an added edge went between a pair of vertices. In step 2, we add two-dimensional, two simplices. But again, the boundary of our two simplex, in this case, the boundary is a cycle consisting of 3 edges. So in order to fill in a triangle, these 3 edges must exist. So I can't fill in a triangle over here because I don't have an edge that connects these. Since I don't have an edge here, I can't fill in this triangle. So no triangle over there, but I can fill in this triangle here. I can fill in this triangle. Let me also fill in this bottom triangle over here, this side triangle, this side triangle, this side triangle, and I've just formed the boundary of a tetrahedron over here. So by adding these 4 faces, so these 2 simplices, I've got the boundary of a tetrahedron. Note, I have to have a cycle consisting of 3 edges, exactly 3 edges. That's the boundary of a triangle. So if I have these 4 vertices along with these 4 edges forming a square, I'm not allowed to fill in that square unless I add another edge. Then with that edge, I can now fill in these 2 triangles, getting a square. But I need to only fill in triangles. I'm not allowed to fill in squares. I have to have 3 edges forming a triangle in order to fill in my 2-dimensional face. So I can get this square right here by filling in these 2 triangles. So these 2 triangles, their union will form a square, but I have to fill in 2 triangles to create that square. I'll also fill in this triangle here, these 4 triangles I'll fill in here, so that I've now just created the boundary of a pyramid with square base. So that gives us our 2-dimensional simplicial complex. As in our step 2, we added 2-dimensional 2 simplices, assuming that the boundary of the 2 simplex already existed. We can now, in step 3, add 3-dimensional 3 simplices. The boundary of a 3 simplex, that's a tetrahedron, is a cycle consisting of 4 2-dimensional faces. Well, remember, we filled in the bottom face and the 3 side faces here, so we did have a tetrahedron here, so we can go ahead and fill in this tetrahedron to get a nice solid 3 simplex, a 3-dimensional solid tetrahedron. I can't fill this thing in, so this is not a tetrahedron. Remember, the boundary of this was a pyramid with a square base. A tetrahedron, all its sides are triangles. I've got a side that's a square over here, and so I don't have a tetrahedron, so I cannot fill this in, and so we'll just have one 3 simplex. And so in this case, we now have a 3-dimensional 3 simplex, formed by adding this one tetrahedron in our step 3 of adding 3-dimensional 3 simplices. In our step 4, we add 4-dimensional 4 simplices, but the boundary must exist. And to create the boundary of any n simplex, we just go from our simplex and remove one vertex at a time. So 4 simplex would be denoted by 5 vertices, v1 through v5. If I want to get its boundary, I can remove the vertex v1 to create this tetrahedron. So remove the vertex v2 to create this tetrahedron, remove the vertex v3, v4, and v5, And so the boundary of a 4-simplex will be the sum of 5 three-dimensional tetrahedron. Well, I only have one tetrahedron, so I don't have the boundary of a 4-simplex, so I cannot add a 4-simplex. And in step n, we add n-dimensional n simplices. But assuming that the boundary of the n-simplex, which is a sum of n-1 simplices, exists. In our example, the highest dimensional simplex that we have is a 3-simplex, this solid tetrahedron here. So we have a 3-dimensional simplicial complex. This partitioning of an object into 0 simplices, 1 simplices, 2 simplices, etc. is called a triangulation. An object that has a triangulation is called a simplicial complex. Let us now triangulate a couple of familiar examples. We'll start with the circle. So our step 0 is to add 0-dimensional vertices, 0 simplices. Let's start by trying to add just 2 vertices. But then in step 1, when we add 1-dimensional edges, if I try adding these 1-dimensional edges here, well then I have multiple edges. We are not allowed multiple edges. So my step 0, I'm going to need to have at least 3 vertices. So we'll add our 3 vertices in step 0, and then in step 1, I can now add these 3 edges. Note that my edges do not need to be straight lines. A curve is topologically equivalent to a straight line segment, so these 3 arcs here are all edges. And so I now have a triangulation of the circle. Let's now triangulate the disk. In step 0, I again add 0-dimensional vertices, so 0 simplices, these 3 0 simplices. Step 1, add my 1 simplices. And then in step 2, I add a 2-simplex. Note that this 2-dimensional face is really a topological triangle. Its boundary consists of 3 edges. Recall that a triangle is topologically equivalent to a circular disk. So as long as I have 3 edges forming a cycle, then I can add a 2-dimensional face. So I do have a topological triangle. I do have a triangulation of the disk. We will now triangulate the sphere. Again, step 0, add 0 simplices, 0-dimensional vertices. Step 1, add edges, 1-dimensional edges, 1 simplices connecting pairs of vertices. And in step 2, we add the 2-dimensional faces, our topological triangles. So I've got this triangle here, this side triangle, the triangle in the back, as well as my bottom hemisphere. This bottom hemisphere is also a triangle. I can tell that it's a triangle because its boundary consists of exactly 3 edges. In case you don't see that, recall that a circular disk is topologically equivalent to a triangle. So we have a topological triangle. If you ever find topology frustrating, well, there is an outlet. I now get to punch my topological triangle in order to form the bottom of my hemisphere. So I've had this disk, I punched it, and so I've created a hemisphere rotating at 90 degrees. I now have my bottom hemisphere is a topological triangle. So we do have a triangulation of the sphere. Note that a sphere is also topologically equivalent to the boundary of a tetrahedron. So I could fill in the boundary of the sphere with a 3-simplex, a 3-dimensional tetrahedron to create the 3-ball. Let's now discuss cell complexes. You don't need to know anything about cell complexes, so you can stop this lecture here if you like, but it is good to know that there are different ways of building things. In some ways, cell complexes are easier, but most computational software will use simplicial complexes. Note that the building blocks for cell complexes are similar to that for simplicial complexes. We still have zero-dimensional vertices, our zero cells. Our one cells are one-dimensional edges. Our two cells are two-dimensional disks, but a two-dimensional disk is topologically equivalent to a two-dimensional triangle. We also have three-dimensional balls, so filled in, but this three-dimensional ball is topologically equivalent to a three-dimensional tetrahedron. For simplicial complexes, we had zero-dimensional vertices, one-dimensional edges, two-dimensional triangles, which are topologically equivalent to disks, as well as solid three-dimensional tetrahedron. To go from the boundary of the tetrahedron, so to go from the boundary of the tetrahedron to the solid three-dimensional tetrahedron, I fill in the tetrahedron, the boundary, with this three-dimensional ball. So whether I have a three-dimensional ball or a solid tetrahedron, we have similar objects. And so the building blocks are basically the same for both simplicial complexes and cell complexes. But the rules for building cell complexes are much more lax than those for building simplicial complexes. We're allowed a lot more freedom when building cell complexes. We will illustrate with a couple of examples. To distinguish cell complexes from simplicial complexes, I'll now color my two-dimensional faces light brown instead of blue. So if you see light blue faces, then we have a simplicial complex. If you see brown faces, then we have a cell complex. We can use whatever color we want. The simplicial complex for a disk consisted of three vertices, three edges, and one two-dimensional face. For a cell complex, I will only need one vertex, one edge, and one two-dimensional face. For both simplicial and cell complexes, we still follow the rule of adding objects one dimension at a time, starting with the lowest dimensional object. So we'll start with step 0 of adding a zero-dimensional vertex. Then at step 1, we'll add a one cell, a one-dimensional edge. For simplicity, I will take the closure of the edge, i.e. I will throw in its boundaries. So we'll throw in the endpoints right here. Since I start off with a vertex, to add the edge, the only rule I need to follow is that I must glue the boundary of this edge to my zero-dimensional simplicial complex. Since I only have a single vertex, that means both the endpoints must be glued to the single vertex, and so thus I am required to add a loop right here. So this entire boundary had to be glued to the vertex, and so we get a circle. Note that the circle consists of a vertex and an open interval right here. Note this is rather different than for simplicial complexes. For simplicial complexes, I was not allowed to have loops. Loops were not allowed. But with cell complexes, I am allowed loops. So to add an edge, the only rule is that both of the vertices must be glued to, so both of these endpoints, the boundary, must be glued to some vertices. So must be glued someplace to the zero-dimensional previously created simplex. We can now, in step 2, add the two-dimensional face, the two cell, and I will again follow the rule of gluing the entire boundary to my previously created one-dimensional simplex. So our basic rule that we need to follow is whenever we add a cell, the entire boundary of the cell must be connected someplace, so nicely glued someplace to anywhere in our previously created simplicial complex. So as long as we nicely glue the entire boundary, we are good. For definition of nicely glued, see the comments on the YouTube page. So I now have a cell complex for my disk. And note it consists of a zero-dimensional vertex, a one-dimensional open interval, plus a two-dimensional open disk. But note that the gluings were very different for our simplicial complexes versus our cell complexes. But for both simplicial complexes and cell complexes, we still follow the rule of adding objects one dimension at a time, starting with lower dimensional objects. But for cell complexes, when we glue in a cell, the only rule is we need to nicely glue in the entire boundary. Recall the definition of Euler characteristic from Lecture 1. Given a simplicial complex, we just counted the number of vertices, subtracted off the number of edges, and added the number of two-dimensional faces, and this gives us a topological invariant. The same calculation will work for cell complexes. So for example, I can use the simplicial complex of a disk to calculate its Euler characteristic. I have 3 vertices minus 3 edges plus 1 face gives me 1, and so my Euler characteristic for a disk is 1. But I could have instead used my cell complex where I have 1 vertex, 1 edge, and 1 disk. Well, 1 minus 1 plus 1 equals to 1, and so I also get an Euler characteristic of 1. So you can use either simplicial or cell complexes to calculate Euler characteristic. We can generalize the definition of Euler characteristic to higher dimensional simplicial complexes. Let Cn denote the set of n-dimensional simplices in our complex, and we'll use the absolute value symbol to denote the number of elements in a set. So to calculate the Euler characteristic, I can do the number of vertices minus the number of edges plus the number of two-dimensional faces minus the number of three-dimensional simplices. So what I do is I do an alternating sum where I add all the even-dimensional simplices and I subtract all the odd-dimensional simplices. A similar formula holds when we have cell complexes. So if Cn this time denotes a set of n-dimensional cells in our complex, we have the same formula where we have the alternating sum of 0 cells minus 1 cells plus 2 cells minus 3 cells, etc. Let's now take a look at the sphere. The simplicial complex for the sphere had 4 vertices, 6 edges, plus 4 faces, and so we had 4 minus 6 plus 4 equals to 2, so the Euler characteristic of the sphere is 2. For the cell complex, we will find that we only need 1 vertex and 1 disk. So our Euler characteristic using the cell complex would be 1 vertex minus 0 edges plus 1 two-dimensional disk. I get 2 for my Euler characteristic. The nice thing about cell complexes is I don't need as many objects to create the cell complex, so counting them can be easier. So let's now create the we'll create the sphere as a cell complex. As before, we start off with step 0, adding the zero-dimensional vertex. So we added the zero-dimensional vertex in our step 0. Then in our next step, well, our next higher dimensional cell is a 2 cell, and so we will now add the 2 cell. But remember, we need to add the entire boundary. The entire boundary must be glued to our previously constructed cell complex. Since my previously constructed cell complex is a single point, that means the entire boundary must be glued to this vertex. So unlike for simplicial complexes, when I glued a 2-cell, I just glued the 2-cell with a nice one-to-one onto map onto its boundary. But with simplicial complexes, I'm going to crush this infinite number of points. All this infinite number of points creating this boundary will be glued to this zero-dimensional single vertex. And thus, I create the sphere as a cell complex. So we do have that this is a 0-cell, and over here we have a 2-cell. To create that 2-cell, I basically just punched my 2-cell really hard. So punch this 2-cell really hard so that it formed almost the entire 2-cell, almost the entire sphere, so that my 2-cell formed almost the entire sphere except for this single vertex. Note that if I remove a vertex from a sphere, I have something that is topologically equivalent to an open disk. So if I remove this vertex right here, I create a hole in my sphere. I can make this hole bigger and bigger and bigger until I eventually get the open two-dimensional disk. So a sphere minus a vertex is topologically equivalent to a 2-cell. Note first that this cell complex is obviously not a simplicial complex. So we're not allowed to crush an infinite number of points when doing simplicial complexes, but we can do that for cell complexes. However, a simplicial complex will be a cell complex. To see that, note that when we created the simplicial complex, we started off with step 0, zero-dimensional vertices, which we can call 0 simplices, or we can call them 0 cells. I can then add 1 cells, gluing the entire boundary of a 1 cell to a pair of vertices. So I can add these 6 1 cells to create now a 1-dimensional cell complex. And we can then add 2 cells to go ahead and finish off creating our cell complex of the sphere. So a simplicial complex is also a cell complex, but a cell complex need not be a simplicial complex. So why do we use simplicial complexes instead of cell complexes? Well, the answer will become obvious in the next lecture. But in the meantime, think about how you would encode simplicial complexes in a computer program versus how you would encode cell complexes.